So welcome. So we're going to look at this next section, which is on static equilibrium notes. And for those of you who are going to do mechanics or have to do statics, this is a bit of a rite of passage. There's these gateway courses, and in engineering, statics is a kind of gateway course. They teach you, the thing I noticed about engineering that I really kind of liked is that to a large extent they had this attitude of the standard is up here and here's a step ladder and it's up to you to climb it, but here's a step ladder. And with some other subjects there was this sense of the standard is here, are you bright enough to figure out how to climb over this thing? It was a different attitude. In some subjects they're looking for bright people, whatever that means, and in other subjects they're looking for trained people. And I found with engineering there was this sense of let me show you an easier way, you know, which I just thought that was fine. So from what I gather for statics is it's a really high standard. One of the people who teaches it, the main person who teaches it is really he's quite demanding, but he's there for you. You know, he will teach you it. It's just that having taught it, he wants it to be, you know, a certain way. So you've got to embrace it and just get in with it. We're going to lay the foundations for that. I'm not going to show you. He's got some matrices techniques, I think, that make complicated systems quite manageable. What I'm trying to get across to you is the basic physics and then the rationale behind it. So we're going to start off initially about a center of gravity. It had to go somewhere, so they put it in here. And then we'll talk about static equilibrium, and we'll talk about elastic properties of solids. So that's where we're at, and let's go through this a little bit. So center of gravity. So we've done center of mass. Remember, this was COM, center of mass. It's not centimeters. It's the x-coordinate of the center of mass. And we said it was the sum for each mass, the mass times the position with relative to some axis, divided by the sum of all the masses. And the center of gravity is basically the weight of each mass times its position divided by the total weight. So mass times position divided by total mass, weight times position divided by total weight. What's the difference? Well, mass is not the same as weight. Weight depends upon the gravitational field that the mass sits in. In this room, if I was to take an object and say, where's its center of mass? I could find it. Where's its center of weight? It's the same place. But the reason for that is that it's in a uniform gravitational field, where the pull, the weight of one little bit of mass is exactly the same as the weight of an equivalent piece of mass over here, because the gravity pull is the same. But imagine that that's the Earth, and so imagine that that's the Earth, and now I have an object that looks like that. Now, I can take a little bit of mass here, and the weight is quite strong. And I can take a little bit of mass there, and the weight is not so strong. So the center of mass would be in the middle, of course, because it's a uniform density, and it's a uniform rod, for example. But the center of gravity would not be in the middle, because this near end weighs a lot more. Kilogram of mass for kilogram of mass than the far end does. So my center of gravity would be here, and my center of mass would be there. And so we'd like to be able to think about that a little bit. Astronomers deal with this when they're talking about galaxies colliding and the like. And but you know, if you're building a bridge across a little stream, I don't think it matters. You know, if you but we need to know about it. So we say the center of mass is that, and the center of gravity is that. And remember, they look similar, so we don't want to get them confused. So we say a 2 kilogram particle is located at +3. So let's do a little drawing. So there's +3 meters, and that's 2 kilograms. And then a 6 kilogram particle is located at +8. So that's +8 meters, and that's 6 kilograms. And the gravitational field strength is given by, so G is equal to minus 12 over X. Okay. What do I feel about the minus 12? It means it's pointing in that negative direction, so we'll just work through it. Okay. So where is its center of mass? So X for the center of mass is equal to the sum of each particle's mass times each particle's position over the sum of each particle's mass. So that's going to be, well, the mass is going to be 2 times 3 plus, it's going to be 6 times 8 over, and it's the masses I'm adding, so 2 plus 6. So that's going to be 6 plus 48 over 8. So that would be 54 over 8, which equals 5 eighths of 40, 6 eighths of 48, 6.75. 6.75 meters. So here, if that's 3, 4, 5, 6, 7, 8, and I'm up here at 6.75. So there's my center of mass, because it's nearer to the 6 than the 2. Yeah, there we are. Makes sense. X center of gravity is equal to, and you know, frankly, I just crossed my mind actually, but it might be worthwhile writing down, you know, WIXI over the sum of WI, because that's easy to remember. And then you know that that is going to be, oh, well, that's going to be MIGI times XI over the sum of MIGI. And then we're doing the sum. And we're going to say it's going to be the first mass, which is 2, times the first gravity field. And the gravity field is minus 12 over its position, which is 3, times its position, which is 3. See where that comes from? I'm substituting my X value, which is 3, into this minus 12 over X. I got a little alarm bell going off in my head, but I'm going to ignore it because I can't think of, I'm just going to see what the answer comes out and then I'll worry about it. And then for the next one, it's going to be the 6 times its gravitational field, which is minus 12 over 8 times 8. I'm going to divide this by the sum of the weights. So it's going to be 2 times minus 12 over 3 plus 6 times minus 12 over 8. So I'm just check on that again. Yeah, that makes sense. Yeah, that makes sense. Yeah, I think that's right. It's just a whole bunch of numbers that are a bit of a pain. On the top, I can cancel those two out, and I'm going to go minus 24 added to, because it's a sum, and I cancel those two out, and that's going to be minus 6 12 is 72. And then on the bottom, I have minus 8 added to, and that goes, well, let's have a look. 6 12 is 72, and 8 goes into 72 9 times. That was very nice. So I have minus 9, which equals minus 24 minus 72 is going to be minus, what's it going to be? 96. Minus 96 over minus 8 plus minus 9 is minus 17. And I'm relieved because I got a positive answer. That's what I was worried about. But the sign takes care of itself. If you know the physics is right, and you're putting numbers in, the math takes care of itself most of the time, you know. So it's good to have the alarm, but 96 divided by 17 is equal to, so this is going to be 5.65 meters, and that is 3, 4, 5, 5.65 meters, center of gravity. Cool. So I think it's actually good. I think we've developed something today. You know, it's for center of mass, it's each mass times its position added together, divided by all the masses added together. And for the center of gravity, it's each weight times its position added together, divided by the sum of all the weights. And we know that weight is equal to mg. Yeah. Either way. Cool. Okay. So we did that. If you remember center of mass, I went off and did a whole bunch of other things. I started integrating, you know, triangles and all that. We're not going to do that. Life's too short. We've got other stuff to do. We're going to do static equilibrium. So this is, it seems like, you know, we keep making 2 steps forward and 1 step back because we're back at equilibrium again. And I thought we'd done equilibrium when we said the sum of the forces. We said the sum of the forces equals 0, and that's equilibrium. And when it's not equilibrium, the sum of the forces is equal to ma. That was Newton's law, and we did that, like, you know, days ago. So why are we back with equilibrium? We're back with equilibrium because although this is a good rule, it's true, it's the law, it doesn't cover all contingencies. Ask yourself this situation. Say you're looking down from above, and let's say we have one team of workers pulling that way. I'm looking down from above. I'm not looking horizontal. I'm looking vertically, and I have one team of workers pulling with a force like that, and I have another team of workers pulling with a force like that. According to this, the sum of the forces vertically is equal to 0. And it's true because plus F added to minus F equals 0. You just look at them. They're all in the vertical axis. There's no horizontal forces to speak of. So the implication is that this object will not accelerate. Agreed? That's what equilibrium means. Not that it's not moving. It's moving around the center of the Earth. It's moving around the sun. It's moving around the center of the galaxy. It's moving, but it's not accelerating. Yeah. But you know what's going to happen, don't you? It's going to go like that. And it's going to go like that kind of quickly. We're going to get an acceleration, but it's going to be an angular acceleration. Okay? And yeah, eventually it'll stop. Eventually when we get to here, if we're still holding on, then, you know, that's going to, and we're not going to get any more rotational motion at that point. But we did have rotational acceleration to get to that point, and it wasn't predicted by Newton's laws to do with force. And so people said, you know, if we want things to be truly in equilibrium, if we want things not to accelerate rotationally as well as accelerating linearly, if I build a bridge or if I put a roof on my house and I don't want it to accelerate up into the air or accelerate sideways or accelerate downwards, then yeah, the sum of the forces is great. But if I also don't want it to, you know, spin, I need to have the sum of the turning equivalent of force. My torques, the sum of my torques must equal 0. So I have 2 conditions. I have that first condition for equilibrium, and I add to it a second condition for equilibrium, which equals that. Because the torque here is a positive torque, and the torque there is also a positive torque, because they're both going counterclockwise about that turning axis. So the sum of the torques also has to equal 0. Yes? Oh, no. You resolve these forces vertically. they're in line with it. There's no component of that force along that vertical axis because it's parallel to that vertical axis. So if I do this, if I do that force, and that force, they all sum together, and that force balances them. It doesn't matter where they are. From a force point of view, from a torque point of view, it matters completely. And that's what we're bringing in here. Yeah, cool. Good question. So this is the next bit we have to do. A lot of the same skills we had before we're going to use again. It's just, you know. So we say the first condition for equilibrium is the sum of the forces equals 0 along a line. And then we say for the second condition of equilibrium, the sum of the torques equals 0 about an axis. And just like in the first equilibrium problems, we had to pick our line carefully. Some lines were better than others from a solution point of view. So we have to pick our axis. Well, we can pick our axis carefully. Remember how we had the old traffic light, and we went through this thing about, well, I could just resolve my forces vertically and resolve my forces horizontally, and I can find a solution. It's a two-step solution, but I can find it. And then we said, well, you know, there's a certain charm. If I want T left, then if I actually put my axis perpendicular to T right, then it goes away, and I can solve it speedier. I've got to do a bit more trig, a bit more geometry, but I can solve it, yeah? It made the problem shorter. We're going to get the same kind of thing here where we have, let's say we have a step ladder leaning against a wall, and there's like forces here, and forces here, and forces here, and forces there. We'll find that although in principle, because this thing is not rotationally accelerating, I can take any turning axis I like. I could take a turning axis through there. I could take a turning axis through there. I could take a turning axis through there. I could take a turning axis through where they both point to. I could take a turning axis through the next classroom. And they will all be the sum of the torques equals 0, because the sum of the torques equals 0 about any turning axis. If it's in equilibrium, it's in equilibrium. It doesn't matter where you decide to analyze it. It's in equilibrium. But if I pick a nice axis, I'm only doing a one-step solution. And if I pick a non-nice axis, I'm only doing a two-step solution. I've got to find another axis and do simultaneous equations. So again, there's a certain benefit in picking a nice axis as opposed to a less comfortable axis. So we say the location of the axis does not matter for an object that is in rotational equilibrium. The net torque is 0 about any point, any axis we like. But to solve it, then some axes are better than others. So if we have two forces, say, acting on an object, then we say, well, the sum of the torques is equal to the torque 1 plus torque 2. And if we have 5 forces, we have torque 5. And if we have 15 forces, we have torque 15. Clearly, that is not the same as that. Clearly. So whereas before we had positive end of the line and negative end of the line, or positive end of the line and the negative end of the line, and even when we worked on a slope, we trained ourselves to say that's the positive end and that's the negative end, even though it wasn't necessarily obvious which one it was. We just decided that's going to be positive, that's going to be negative. Now we have to decide which one of these is positive and which one of these is negative, because one's going clockwise and one's going counterclockwise. And unfortunately, people got here before we did, so they've already decided, and the answer is that the counterclockwise is the positive torque. Yes, I know, a lot of things in physics, and it continues actually in physics too as well. You kind of see this stuff and you go, why on earth did they pick that? And a lot of it comes out of the cross product. The cross product, for some reason, gives me a sense of things working backwards. The order that they're in somehow seems backwards to me. The sign of things somehow seems backwards to me. So there's a number of times in physics when I go, why would they pick that? Well, they picked it, you know, just live with it. So you've got to kind of drill in that clockwise, clockwise is negative and counterclockwise is positive. So, way it goes. There's basically 3 examples that we do, and I think of this a bit like our experience with the circular motion, where there were 4 examples, and I kind of showed you one of each, and then you kind of like, you got one of them basically. I can put my hand on my heart and say they've seen something like this. You know. There's 3 examples that I deal with this. There's what's called a seesaw, or a teeter-totter, or a balanced beam. I don't know, various people call it various things. And then there's sometimes called a boom and a mast, because it looks a bit like a sailboat, or a ruler leaning against a wall. You know. We do a lab on that one. In fact, we might do a lab on the first 2, I can't remember. Depends on the semester. And then the 3rd one is a ladder leaning against a wall. And I think you can see that the complexity tends to get a bit more because there's really more things unsaid. You know, what's going on at this where the string meets the top of the mast? Are the forces there? Do I need to take those forces into account? What's going on where the mast meets, where the boom or the plank meets the mast or the wall, whatever you want to call it? What's going on there? So, and then with this ladder, what are the forces at the bottom, what are the forces at the top, what's going on? So it seems to get more complicated as time goes on. It turns out mathematically it's not that much more complicated. In fact, the first one has a lot of hidden math in it that we don't think much about. We don't get to trusses, you know, bridge sections. I bought when I was buying a house, I was single, and I bought a little house next to Publix, and my realtor tried to talk me out of it, and she said you're in the wrong school district, and I said I'm single. Why would I care? I got Publix over there. I got, you know, Blockbuster Video, shows you how old it is. Blockbuster Videos down the road. You know, it needed work, and I wanted to be a fixer-upper, so Home Depot was there. It was great. And then within a year, I'd met my wife, and within 2.5 years, we'd had a child. And I remember she gave birth. She was a little bit older, so there was a lot of counselling about the possibility of issues. And it really panicked us, actually. It was like, man, you know, I didn't realise. It was quite depressing. But she gave birth, and I remember I counted every finger and toe. And I was like, 20 minutes of total elation. I phoned everybody whose number was in my telephone. And then I thought, oh my word, we're in the wrong school district. And I went in to see my wife, and I started saying to her, we got to move. We're in the wrong school district. And she's going, you know, we got about 5 years before we need to worry about that, you know. But anyway, she started working on it pretty soon. And then one day, we lived down here. We lived basically, I had the cheapest house on Hawthorne Road, which is just north of Gandhi. It's just north of Gandhi. It's next to the Publix. My house was like the cheapest house. And one day, we fixed it up because, you know, we'd put fences up and stuff like that. So it was coming up, and values were coming up in price. And Emily was getting more mobile. And one day we found we had a babysitter occasionally, and the babysitter took her across to Publix. She'd walked back carrying Emily and stood her on the side of the road, and then walked back across the road to pick up the bags and carry the bags across to get to Emily. And Emily's telling us all this, and we're going, what? She left you by yourself? Yeah, she said, don't move. And I'm going, you know. So that kind of put a fear up us. And then one day I came home from work, and my wife says, we're moving to New Tampa. You know, good luck, you know. I know your drive's going to be miserable, but we're moving to New Tampa. So we moved to New Tampa. We found that there was this house we'd seen a year before, and I loved it. And I figured so we moved and we looked, and we saw a house that I loved. And then we started selling our house, but the market was terrible. And this guy was jogging by, and he was living in a rented house, and it was like the house he wanted. So we only showed it to 2 people because it was next to Publix. A lot of people didn't want it. We showed it to 2 people, and the second person bought it. So it was like, yes. So now we're looking. We're going to find a house. So now we're looking. I bet that really nice house is gone. We look, and I don't like anything. And then I said to the realtor, "Is that really nice house still?" "Yes, it is. It's still on the market." We go and look at it. This is meant to be. We go. I get my old inspector. Tom comes. The one who inspected my first house comes to my second house. Because I know that he'll give me the wink and say, "You need to fix this," rather than saying, "I'm not going to give a mortgage thing." He's got to give the clearance. So if I'm there, he'll tell me, "Hey, you promised me you're going to fix this," and he'll let it pass. If I'm not there, he's not going to. If ever you're buying a house, be there for the inspection. Okay, be there with the person. Because they'll sometimes say, "Man, that plug needs fixing," and that can stop your mortgage from going through. But they'll say, "Will you fix it?" You go, "Yes, I'll fix it." It's like, it's a plug. It's like, So he's there, and everything's going great, and he's saying to me, "This is a great house," goes through. And he comes down from over the garage, and he's like pale. And he says to me, "You need to hear this." And he says to the homeowner, "Somebody has sawn through all the joists in the roof above the garage, which means this house is structurally compromised, and it is unsellable as it is." And the guy said, "I was wondering if you'd catch that." And I was like, and his wife had just been telling me how over the garage there was so much storage. Well, yeah, you bet. It cut all the trusses out over the garage. So I'm thinking, the house is gone. And then Tom turns around to me and says, he's going to have to fix it. I don't know if you can wait that long, but he's going to have to fix it. He's going to have to get an engineer to sign off on it that it is up to code. So what they did was I think it's called widows and orphans, where they put, if you have a piece of wood and a piece of wood, what you do is you put a piece of wood on one side and a piece of wood on the other side. And then you bolt it through. So in my above my garage space, there's a whole bunch of that. And that's statics. That's what engineers do. So we don't go near there, but the principles I'm going to show you will get, so that when you do that, I think you can grasp it. Our lab tech, the evening lab tech, has actually just gone through statics. So you might want to talk to her. If you're doing lab and you see her, just talk to her about her experience doing statics. She kind of really liked it. She said it was one of those courses where she felt like she was being pushed like crazy. But at the end of it, you go, "Yeah, he taught me how to do this, and now I can do it." And it really builds confidence for you as an engineer. So it's a good thing. So let's do some of these. So this is the seesaw. And basically what we do is, we've done these before. I suspect you've done these before. A 5 Newton force is located 4 meters to the left of the fulcrum. This is the fulcrum. It's the balance point. And a 15 Newton force is located to the right. And where is it located? Okay. Now I'm talking about newtons, so I'm talking about weights. I could talk about masses, and you should really convert it to weights. But you know what? I bet people don't, and the fact that you didn't put 10 on one side, you didn't put 10 on the other side cancels, so you get away with it. But you should really talk in terms of weights. Forces in this case, so it's weight in this case. And what we say, typically you'd say the sum of the torques about a turning axis equals 0. And then your question is, where should we put the turning axis? Anybody want to suggest where to put the turning axis? Where would you put it? On the fulcrum. That seems the most logical place to put it. So I say it's going to be F times X1 plus F times X2 2 is equal to 0. So we look at this and we go 15. Now, do not invoke a sign because of the force. Invoke a sign because of the torque. So that's pointing downwards, so you might say that's a negative force. But don't even think about it in that way. Think about the turning effect of that force. And is it clockwise or counterclockwise? So do not invoke a sign because the force points in a certain direction. Invoke a sign because the turning axis is clockwise or counterclockwise.
But it's balanced and there's no pointing anywhere.
So, but it won't always be like this. So So we're gonna do this. We're gonna go 5 times 4, and then over here we have 15 times x, and I look at this 5 times 4, and it's very simple. It just seems like, that's going to go in a counterclockwise direction. So that's going to be positive. And then we add it to, and this one's going in a clockwise direction. That's negative, and that sums to 0. Now I'll tell you now. There's times when our turning axis is there, and our force is here. They're not level with each other. And people sometimes have trouble deciding if that's clockwise or counterclockwise. And we'll see that in a few minutes. So it looks easy to begin with, but just be a bit respectful of it, because it's not necessarily as easy as it seems to be. And people sometimes make a mistake, and they're stunned that they made a mistake because it's just clockwise or counterclockwise. And it's just because of the diagram. So then I say, okay, so that means that 20 is equal to 15x. So x is equal to 20 over 15, which equals 1.33 meters. And we're happy. We got our answer. Yeah. And it seems pretty straightforward. Yeah. Now, there's actually a bit of a cheat taking place here that's not so obvious. So it says, let's do this again, and let's do it deliberately taking a different position. So let's pick another turning axis. If the sum of the talks about a turning axis equals 0 when you're in equilibrium, and this is in rotational equilibrium, we should be able to pick a turning axis wherever we like. So I'm going to suggest that we put our turning axis through that 5 Newton force, just because. Let's say it just occurred to me to do it there. Then I would say the sum of the torques about that turning axis equals 0. And now what would I write down for my next line? It would be 5 times, well, there's no separation. 5 times 0. And it doesn't matter what sign I give it, because it's going to be 0. It's not clockwise or counterclockwise because it's not turning. Yeah, agreed? Plus, well, it's 15, and that's 4 plus x away, because it's 4 to there, and then there's another x to there. Agreed? And that has a sign. That's definitely going to be clockwise, so that's going to be a negative, equals 0. And that don't work. That's wrong. Can you see what I've missed? I've missed something. The math on the face of it seems right. 5 times 0, because there's no separation between the turning axis and the force. They're like, there's nothing, there's no gap. So it's 5 times 0. And then it's 15 times 4 plus x. But minus 15, 4 plus x cannot equal 0 unless x equal, well, it can't equal 0. Can't equal 0. There's a problem. I've missed something out. What have I missed out? Sorry?
Would it be unbalanced?
It is unbalanced, so what do I need to do to make it balanced?
So missing a negative? Is it missing a negative?
No, there's something bigger than that missing. It's more physicsy than that. It's not, pardon? Yes. What I missed out because it just didn't occur to me is I got to have a force at the fulcrum. Because if I have 5 newtons down and 15 newtons down, there's 20 newtons down. And if that's all there is, I'm not in equilibrium. Even the sum of the forces equals 0 isn't true. So what happened was I really have 20 newtons in that direction. So that the downwards force is equals the upwards force. But because I put my turning axis through the fulcrum, even though I didn't think about the 20, I'm multiplying something I didn't think about by 0. So it went away. So even though I didn't think about it, it was cancelled out because it's on the axis point. So I was lucky. In some ways I was lucky. I only thought of 2 of 3 forces, and I happened by chance to put my turning axis through the force I didn't think about when I did the red version of this. I really dodged a bullet. Whereas now I didn't dodge the bullet. So I have to be a bit more careful and I have to say, oh, let's go here. I have to add in a third force. So I say plus, now I'm looking at that 20 and I'm saying 20 times 4, and that is going to be a counterclockwise turning axis equals 0. Oh, because there's my turning axis. And that force is going that way, yeah? Yep. So then I say minus 60 minus 15x plus 80 is equal to 0. So that means that 15x is equal to 20, which means x is equal to 20 over 15, which equals 1.33. So the lesson that comes out of this is that you got to be careful that you have all the forces correctly labeled. Otherwise, you might end up with a problem. And it's not going to be given to you. Now, sometimes you're lucky and there's a force you don't think about, or you've been trained. And, you know, I'm sure you've done this before, and they said put the axis through the fulcrum, because what's on the left will balance what's on the right. And it's intuitively, it's exactly right. But you're basically, you're not really doing the sum of the torques equals 0 because you're missing out. Well, you are. But you're lucky about how you did it, you know. Can I show you just one more problem, just because I want to show you just a little bit about, you know, just a slightly more complex problem. Sometimes it comes up, sometimes it doesn't, but I want to show you it's there. So can I erase this? Okay, so in fact, let me do that. Well, no, yeah, let me do this. So let me do that. So then, if somebody wants to look at the very end, they can look at the very end. So I'm going to go there. I'm going to go. Well, they can't. Ah, well. I'm going to go. I'm going to go home. I'm going to go. No, I'm going to go to there. There. No, I'm going to go there. I'm going to go. How do I add a page? New slide. Thank you. And then let's do something a bit more interesting. So slide. 1, 2, 3, 4. I hope it's there. Yeah, it is. Okay. So let's do this. Let's do. Let's do. Let's do 6 newtons, 1 newton, and 2 newtons. Let's do, this is going to be 3 meters And between here and here, we'll have, between here we'll say 2 meters. And then that's x meters. You got to find x meters. You got to find that gap. Yeah. So you'd say the sum of the torques about some turning axis equals 0. And where should we put our turning axis? Yeah, by all means, put your turning axis on the fulcrum. I'm not saying that's a bad thing to do, but you really should be mindful of the fact that that's going to be 9 newtons upwards. You should be mindful of the fact that you're actually, cancelling out this 9 Newton force because you're making it so it has no torque. That's the equivalent of putting the axis at 90 degrees to the string you don't want to be bothered about. That's the equivalent when you put the turning axis through that force. So the 9 newtons is there. We're just going to put our turning axis through it. And so I go 3 times 6. And that's going to be a counterclockwise, so that's positive. And then I go, well, that's going to be 1 times 2, and that's going to be clockwise, so that's going to be negative. And then we have, it's going to be 2 times 2 plus x. And that's going to be clockwise, so that's negative, and that equals 0. So I'm just throwing a bit of algebra in here to kind of just stress you a little bit. So that's going to be 18 plus minus 2 plus, I've got to expand this now, minus 4 added to minus 2x. I took that minus 2 and I multiplied it into the 2 and I multiplied it into the x. So then I get 18 minus 2 minus 4 is equal to 2x. So that's going to be 18, 14, 12. 12 is equal to 2x. So x is equal to 12 over 2, which equals 6 meters. So this here is 6 meters from there to there. Yeah. So it's the same kind of thing, just a little bit more involved, a little bit more interesting. Yeah. So basically, I expanded. I said 3 times 6 is 18. 2 times 1 is 2, and it's a minus. And then 2 times 2 is 4. It's a negative. 2 times x is 2x, and it's a negative. Then I'm letting the math take care of itself. Yeah. Not bad. Okay. So maybe something on that level. So look how we're doing for time. Let's have a look. I got time. This next one, a 4 kilogram uniform, 6 meter long, horizontal beam. If you like, I'm going to do that as 6 meters. The rope makes an angle of 35 degrees with the horizontal. What's the tension in the rope? Where did that come from? Well, there's got to be a force of tension here. By the way, there's also a force of tension there pulling down on this pivot point up there. Are they the only forces in this problem? Are there other forces in this problem I've got to deal with? So first of all, which bit of this diagram will I say is in rotational equilibrium? All of it, I suppose. But I've got to apply the sum of the torques about an axis to something. So I'm really talking about the plank. I'm really talking about the plank. So it's the forces on the plank that matter. And so rather than the tension coming down from the wall, I don't care about that, but I do care about that tension. So thinking now about the plank, what other forces act on the plank? So gravity. So where shall I put this weight? In the middle. Why in the middle? Because it's uniform. So we're going to do that. So that's there. And I can look at this and go, it's 4 kilograms, so that's 40 newtons. There's no secret about that. Are there any other forces? There's the normal force between the wall and the plank. Are there any other forces? The friction force, where the plank touches the wall. I mean, literally, if you think about it, take a ruler and imagine, all right, you're holding one end. What's going on at the other end? Why is that not slipping down? What's stopping that from slipping down? And it's like, there must be a frictional force upwards. And you only get that frictional force upwards if there's a slight push in. Oh yeah, there's a normal force. There's a normal force and a frictional force. Why is the frictional force upwards and not downwards? So frictional forces tend to oppose motion or the tendency to motion. And the tendency to motion is downwards, so the frictional force must be upwards. So I need another force, don't I? And I need a frictional force. Oh man. Any other forces? No. There's no normal force at the other end because it's not pushing against anything, I got 3 unknowns. This is a disaster. This is like I got 3 unknowns. I need 3 equations to solve this if I'm going to just do it by plug and chug. But which one do I want? Tension. So this is what you do. And I would recommend you literally do this. You put your pen over what you don't want. Because if you put the turning axis anywhere on here, that force has no torque. Agreed? When you put the turning axis through the force, when you put the turning axis through the force, it goes away. It's got no torque. Yeah? So if I don't want to talk about Fn, put my turning axis somewhere on that line. And if I don't want to talk about Ff, put my turning axis through that line. And where they cross, I forget about both of them. So, man, if I just put my turning axis, let's change colour pens. If I put my turning axis through there, Fn goes away, Ff goes away. Happiness. Yeah. So I say the sum of the torques about my turning axis is equal to 0. So I can say, oh, now, torque. I know my distance from my turning axis to the beginning of the string is 6 meters. What force, letter, I'm going to use a letter. What will I write down to get the torque caused by this force about that turning axis? What's the expression that I'm looking for? Is it T times 6?
Sine.
It's going to be T sine 35. Because what I've done is I've said, oh, torque is the perpendicular force. And so I chose to do the perpendicular force times the lever arm in this case, yeah? So you get it? It's not just any old force and any old distance. It is the force that's perpendicular to the distance or the distance that's perpendicular to the force. And we did that for our talks. Not it's F times R times the sine of the angle between, and the sine of the angle between, in this case, there's my F, and there's my R, and the sine of the angle between is 35. So that's that, and that is going to be, is that a clockwise or a counterclockwise tendency? Counterclockwise, so that's positive. Added to, now I'm looking at this 40. It's going to be 40, and the perpendicular distance is 3, not 6, it's 3. And that's going to be a clockwise tendency. So T sine 35 is equal to 120 over 6. So T is equal to 120 over 6 sine 35, which equals 6 sine 35. I did that right. 34.9. There we have it. So if you pick the best axis, it's not hard. It's one-step solution. There's a little bit of trig in it. Can you see how if you don't draw a diagram, you're kind of done for? I don't see how you can do that without a diagram. It's like, it's... but if you draw a diagram and you're fundamentally remembering that your torque must be a perpendicular force times a distance, however you get there, then, so you've got to use a component, then it works out. Yep. But this is not the only version of this problem that I can ask. So I'm going to change color. And let's just set up a few situations. Supposing I asked for FF, where would you put the turning axis? B. And what you're going to do is you're going to say, I don't want Fn, so you're going to put your thing there, and I don't want T. Oh, it's going to be at that point. You can solve it if you put the turning axis anywhere. As long as you keep doing it, you can get 3 equations, 3 unknowns. But man, that saves you a lot of work. And let's change colored pens. Let's go to purple. So supposing I ask for Fn, where should turning axis be? Where would you put it if I'm asking you for Fn? So if I'm asking you for Fn, I don't want Ff, yeah, and I don't want T, and they cross there. And my distances are all different, you know. The forces, I got to look at this, I got to analyze it and say, well, let's have a look. That 40, it's not level. That 40 there is not level with that turning axis, but it's 3 meters away from it. So that's going to be 40 times 3, and it's clockwise, so it's minus 40 times 3. But then this guy, if I'm trying to find, what am I trying to find here? Fn. So now this Fn is here, and it's that far away. And I got to work out what that is. If this is 6, and that's 35 degrees, opposite over adjacent is tangent. So this is 6 tangent of 35 degrees. So I'm doing some trig. So there'll be some playing around with trig, but, you know. And again, without a diagram, just forget it. It's not going to happen. So, and if I asked you, I might ask you something like this, but supposing I asked you for the coefficient of friction. You'd say the coefficient of friction equals FF over Fn. Yeah. FF equals mu times Fn. So mu is equal to FF over Fn. And then you'd work out what your FF is, then you'd work out what your Fn is, and you'd get your answer. It's a long question. It's a longer question than, you know, I've asked it occasionally, but it's a longer question. But it's quite doable. It's just a bit long, you know. So yeah, you know, learn the approach. The example I've given you is one of 3 easy possibilities. But I'm not going to do a tapered stick. I'm not going to do a triangle. I'm just going to do a uniform stick. Yeah. Let's have a look. How are we doing? We need to stop, I think. So yes, we do. So let's stop.